We introduce a Noether theorem which connects symmetries and conservation laws. We derived the Noether theorem in the case of classical fields, but usually the symmetries of the classical theory are the same as in quantum case. In some cases it's not true, but most of the time it is. Noether theorem only applies to continuous transformations, not discrete transformation like parity, for instance. To derive the Noether theorem, we introduced infinitesimal transformations so that our transformations are linear in lambda. The transformation is a symmetry only when the Lagrangian transform at most to a term proportional to a covariant derivative del mu f mu. In that case, the action is transformed by only a constant, and because of the stationary action principle for classical field theory, that will not affect the equation of motion. The theorem stipulates that for each symmetry there is a conserved current, conserved in the sense that its covariant derivative is zero. That's true for Lagrangian, which can be function of more than one field. So here it's expressed for n fields in total. And the resulting conserved current has a time-like and a space-like components. So it's a 4-vector, which obeys the continuity equation. And that's a consequence of del mu j mu equal to 0. From this we can also extract a conserved charge, really conserved in the sense does not change in time, and that's a space integral of the time-like component of the 4-vector current j mu. We saw some applications of Noether theorem. The first one was to the case of a global gauge invariance, when we change a field by a global phase. That doesn't change Lagrangian, and in that case we worked out a current, conserved current in this form. We also looked at the case of translational invariance. In that case we transformed the coordinate itself. A mu is the direction of the translation in space-time, so we can choose to translate in time only, or along x, along y, along z. We worked out the conserved charge, which is proportional to a quantity we introduced as the energy momentum tensor. We then obtained 4 conserved charges. The first one is the energy. It is a space integral of a quantity which we identify as the Hamiltonian density, and which also involves the canonical momentum expressed as the derivative of the Lagrangian with respect to the time derivative of the field. The other 3 conserved charge are the 3 components of the Euclidean momentum, which is also expressed as function of the canonical momentum and the space derivative of the field.